How's it going, folks? I want to take a little bit of time to go over your recent quiz on chemical bonds. Before we get started, something that's going to help clarify a lot of these questions as we go through them is actually the follow-up questions at the very end of the quiz. So I'm going to scroll down here a little bit. So I went ahead and wrote in these answers, but what type of bond do a metal and non-metal form? Typically speaking, that's going to be ionic. Uh, the exception to this is that hydrogen can bond ionically, but typically speaking, it's kind of either or. But again, we'll go through these questions one at a time. As far as two nonmetals, number two, that's covalent. So one of the first things we're going to do before we start trying to draw anything is we're actually going to first try to figure out, is this ionic or covalent? And again, we're going to do that before we name them. So first things first, this MgF2 here. So what we're going to do is we're going to write in ionic, because again, this is magnesium and fluorine, which you can see here on the left hand side, group 2, magnesium, right side, group 17, fluorine. So that means that as far as number of valence electrons, magnesium is going to have 2 valence electrons, and fluorine is going to have 7. Okay. So what we're going to start off by doing is just kind of drawing those in on the original 3. So one of the mistakes that I've noticed a lot of people make is that they're only following this first example of sodium chloride up here at the top, where they have one here and one here, right? So there's 2, right? The only reason there are 2 atoms there because there's 2 atoms in the compound, right? So whenever we're looking at magnesium fluoride, we need to acknowledge that there are 1 magnesium and 2 fluorine. Right, so first things first, we're going to go ahead and draw in our valence electrons. I'm going to zoom in a little bit here. So for fluorine, we decided that was 7, right? 1, 2, 3, 4, 5, 6, and 7. I'll go ahead and do that on both of those. And for magnesium, we decided there were 2. We'll draw those up here at the top. Alright, so the next thing that we're going to do here is, because this is ionic, we know that this is going to be the transfer of electrons. So we're going to change over my pen here real quick. These electrons, again, following the octet rule, that fluorine wants to have 8 valence electrons. So we're going to draw these as leaving, right? So those 2 electrons, they will leave magnesium and they go to each of these fluorines. So what you're going to end up having is, rather than have 7 fluorines, or 7 valence electrons on fluorine, you're not going to have 8, so it's fully satisfied. All right, and that's going to be the case on both of these. I'm not going to draw any electrons on magnesium, though, because again, it only had 2 valence electrons, and those left. An important thing to note, let me pull up my periodic table for you guys real quick. An important thing to note is that we're counting valence electrons, not total number of electrons, right? So here you see magnesium with atomic number 12. If you remove those 2, you're going to go back, and from an electron point of view, it'll have the same number of electrons as neon does over here, which is atomic number 10. Right, so it lost those 2 electrons. It had 12 protons and 12 electrons. It lost 2 electrons. So it now has a full outer energy shell, a full valence shell. But we don't really need to draw those. We're just going to leave it like this. So that's what we're looking at there. As far as naming it, ionic compounds are going to be your easiest ones to name, right? So you take the first one, that metal, magnesium. Pardon the handwriting here, folks. Magnesium, and then the only thing we're going to change for fluorine is we're going to change the end of that word to IDE, right? Magnesium fluoride. Now, the reason we're not including any Roman numerals or anything here is because magnesium only ever has a charge of +2. If this was iron fluoride, we would have to specify whether it was iron 2 or iron 3 because it has what's called multivalent. It can have different charges, but magnesium is simple. It's just positive 2 that it forms. While not required, it really helps your case, especially whenever you do these ionic drawings, to then go ahead and include what the charge is. So for this is -1, -1, and +2. Right? So that's our ionic one. That's magnesium fluoride. We're going to go ahead and scroll down to the next one, which is strontium bromide. Keep in mind, to save a little bit of time on the video, I did go ahead and fill in these atoms as they're pictured here. On your paper, you didn't have that first. What you were looking at first is just a name, right? So strontium bromide. I'm going to cycle back over to my periodic table here. Strontium is in group 2, right? Fluorine we worked with already. That's group 17. So if you look at this from a ion point of view, just like as far as valence electrons go, it actually is going to look. I'm sorry, I said bromine. It's in the same row as fluorine. It's just 2 periods down, but it's number 35 right here. Because these are in the same rows as each other, from a valence electron point of view, they're actually going to end up being the same. So +2 for strontium and -1 for bromide for each one of these. So what we're first going to start off with, we'll go ahead and write that out over here on the right. SrBr2. One of the main things that I saw people do on this test is that they would just have SrBr. They wouldn't have 2 bromine. Please make sure you guys are following the charges of things. That ion cheat sheet would go over what the expected charges would be for those +2 and -1. In order to balance those out, again, we want our compounds to be neutrally charged. That would be the logic that we would follow. And again, because this is a metal and a non-metal, we know it is ionic. All right, so same thing as before. We're just going to zoom in a little bit. Because this example is pretty much the same, I'm going to run through that a little bit faster and just plot out these electrons on the faster side. Right? So again, strontium, just like magnesium did in the last example, is going to transfer out 2 of its valence electrons and become positively charged. Right? So I'll zoom in and draw my arrows here. So it's, not what I meant to do. So first one to here, second one to here. So again, our drawings are going to look very similar between these two, right? We're just really swapping out the chemical symbols. And that was meant to kind of give you guys a little bit of a freebie. I know strontium and bromine are not as frequently used as magnesium and fluoride, but the logic is pretty much the same as far as how those are completed. So up next, we have water. But something really important to point out here is that water is a covalent molecule. We talked about water being a polar solvent, and keep in mind that polar is a designation you give to covalent compounds. A lot of people were saying this was ionic, but it is. Keep in mind, hydrogen is a non-metal. So hydrogen and oxygen, while hydrogen can bond ionically, this is not one of those exceptions. This is just your typical everyday covalent bond. So something new. This is our first covalent of this test. How we name covalent compounds is different from how we name our ionic compounds. So while it's very natural to want to call this water, that's not the name of the compound. That's just the colloquial term. That's just the typical English term for it, and that's fantastic. It's great that you guys recognize it. But the test here is asking you to use the naming conventions that we learned, the nomenclature that was detailed in our PowerPoint and in Explain Chemical Bonds 5. So there are, after you're reading this, there are 2 hydrogens and 1 oxygen, right? And we know that because it's H2O. A lot of people were drawing this assuming that 2 was saying that there were 2 oxygen, but no, it is attached to the hydrogen. Those subscripts go on the right side, right? So over here on the left side, we would call that dihydrogen. dihydrogen, and then monoxide. Pardon me with the technical difficulties. I'm going to type this one out. There we go. A little bit easier. Sorry, getting used to the pen still. Okay, so dihydrogen monoxide, right? That would have been the answer that you guys got. Again, not water. Yes, it is technically water, but that's not the compound name. So we're going to start off by drawing in our valence electrons, right? So first things first, we're going to go over to that periodic table. We see hydrogen is in group 1, so it has 1 valence electron. Oxygen is in row 16, group 16, so that's going to be 6 valence electrons. Keep in mind for 13, 14, 15, 16, 17, all these nonmetals over here, we're really ignoring the tens place here. So 13 has 3 valence electrons, 14 has 4, 15, 5, 16, 6. All right, so we're going to ignore that tens place. So I'm going to go ahead and zoom in and draw these out a little bit. All right, so first things first, we're going to draw our valence electrons on hydrogen because they're super simple, right? It's just 1 apiece. We decided for oxygen that it was 6. So typically we draw these in pairs. Something you can choose to do if you see this compound, you know what your next steps are. What can make things a little bit easier to draw is when you know 2 things are about to bond, especially covalently, you can draw them on the side here, and it makes it a little bit easier to track as you're going through. So covalent bonds, keep in mind we're not going to be drawing an arrow. We're not going to be drawing an arrow because it's not really transferring that electron, right? So we're going to back that out. We're not transferring that electron. What we're doing is sharing those electrons, right? So these 2 on hydrogen, this one on hydrogen, this one on oxygen, are going to share together, right? So we're going to go ahead and draw ourselves a little bond over here, right? Same thing with the one on the left side. You have 1 valence electron on hydrogen, and it's going to share one of those valence electrons with oxygen. Keep in mind that the only exception to the octet rule that I made you guys learn was hydrogen. Hydrogen is fully satisfied having 2 valence electrons, and I'm going to show you guys a periodic table to explain why. Right, so here's our periodic table. Here's hydrogen at the very top left. When the valence shell is full, it's over here in this row with the noble gases. So helium is a noble gas, right? So hydrogen, from an electron point of view, is a lot like helium once it has those 2 valence electrons. So it's pretty satisfied once it has 2, right? So let's back this up. All right, so this would be all we needed to do is from a bond point of view, but keep in mind we want to make sure we are tracking all of our valence electrons. So we still have 4 more for oxygen. So what we're going to do is we're going to put them right here and right here, right? So if we were counting these out, which I won't do this for every one of your examples, but I'll do this for the first one, is to make sure you guys understand the point. Make sure you understand the point of these bond lines, right? So it's telling you that right here is an electron, right here is an electron, right here, right here. So on each side of this line is an electron. If we count these out, we have 1, 2, 3, 4, 5, 6, 7, 8. That's 6 from oxygen and the 2 from hydrogen, right? Because remember, there's 2 hydrogens, 1 piece. So that's water. And again, the reason it takes this shape, if you drew this in a straight line, I would give you credit for that. This particular example, they did go over and explain part 7, where Hank Green was talking about the polarity of water and how these electrons are not evenly shared. But again, that's not something I'm requiring you to know for this exam. All right, so for your next example here, you have N2O4. Let me change this back to normal so don't forget. So N2O4, it says covalent on there. I went ahead and gave you guys that answer, but something, again, that a lot of people were skipping. Some people were saying nitrogen oxygen or nitrogen oxide or nitrous oxide, and that's great that you guys are able to recognize these chemical symbols, but again, covalent bonds, you need to be using your Greek prefixes. So over here, I'm going to go ahead and type this out, but this would be dinitrogen tetroxide. Make sense? So di is the Greek prefix for 2, because again, there's 2 nitrogen, and tetra is the Greek prefix for 4. Again, when you have those, have something like oxygen where it's starting with a vowel, a lot of times you'll drop one of those two. So instead of tetraoxide, you say tetroxide. If you put tetraoxide, that's fine. I would give you those points. But again, something that's worth noting. Okay, so I've drawn out our 2 nitrogen and our 4 oxygen. But keep in mind, this is one compound. All these things are going to end up attached together, and a lot of people were drawing these as 2 different molecules, each of them being NO2. But no, this is all one. So I'm going to start by opening up our periodic table. Find nitrogen and oxygen. Here they are over on the right side. You have nitrogen in group 15, so that's going to be 5 valence electrons. Oxygen in group 16, so 6 valence electrons. So if we want to be really good students, what we're going to start off doing is adding all those up. So 4 times 6, which is going to get us our 24 valence electrons from oxygen, and 10 valence electrons from nitrogen. Again, 2 times 5. So if we want to add those up, we have what? That's 34. 34 valence electrons. Don't worry, guys. One of these days I'll get good with the pen on here. Okay. All right. 34 valence electrons. So we're going to start off by plotting those out. And again, yes, this might take a second, but ultimately it is a worthwhile skill. Ooh, we scrolled up a little bit. Okay, so here we are back at our example. I'm just going to zoom in a little bit and add those electrons. So then we decided it was 6 for oxygen. 1, 2, 3, 4, 5, 6. Same with this one. 1, 2, 3, 4, 5, 6. And we're just going to sprinkle those around a little bit. Now, if you were doing these drawings and you weren't including the circles, you were just doing like the letter O and the letter N with these dots around them, that's perfectly fine. That's another very common way to do this. I just chose to use the circles to match the examples that were given as part of the test. Right, so let's go ahead and add these 1, 2, 3, 4, and 5. 1, 2, 3, 4, and 5. Oh, well, I guess I'll make those symmetrical for all those OCD students out there. I'm probably driving crazy here. All right, so if we go through and count these, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34. All right, 34 valence electrons. So we know we have all of them accounted for. We're trying to figure out how we need to rearrange these in order for them to share the octet rule, or in order to meet the octet rule. So one of the reasons that we start off by counting those 34 valence electrons is that where we locate these, keep in mind these electrons can flow between all these atoms that are sharing them. So where they are located can sometimes be a little bit tricky. So we're going to start off just doing a single bond between everything we have here. Right, so these nitrogen attached to these oxygens. Whoop, that was a squiggly line. So these are all single bonds, right? So if we count these, we have 2, 4, 6, 8, 10. We have a total of 10 electrons out of those 34 total, right? So if we start off coming over here, and we just start plotting these down. So that was 10, here's 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, and 34. Which this would be great because we've accounted for all of our electrons now, but there's a little bit of an issue, and that issue lies with the nitrogens here in the middle. They, well, again, they only have 6 valence electrons as this is drawn. We didn't go into this, and while some compounds will allow that with nitrogen, I told you guys from the get-go that we weren't going to have any weird exceptions to the octet rule. So, um, there are going to be some double bonds here, but they might not be where you expect them to be. So I told you guys earlier that these electrons can flow between all the atoms that are sharing them, right? So there's not a guarantee that you're going to have one atom give off or share one of its electrons and another atom share one of its electrons. Sometimes you'll get 2 from the same one. So what I'm going to do over here, I'm going to take my eraser, and I'm just going to erase these 2. Again, both of those from oxygen, and give that a double bond right there, right? I'm going to do the same thing again to another one on the left side. Again, it doesn't matter if you do top or bottom. We'll do bottom for this one just for aesthetic purposes, but let's go ahead and take that right there. So again, I erased 2 electrons from the bottom left oxygen, and I put those right here, right? So now we can go through and count these again and see if we come up with the same number, right? So if we look at just bonds first, we have 2, 4, 6, 8, 10, 12, 14. And then we have 16, 18, 20, 22, 24, 26, 28, 30, 32, 34. So now we have all of these. Alright, so we're going to keep on moving down a little bit. So nitrogen. Nitrogen, again, it's a non-metal, so a non-metal to a non-metal is going to be covalent. Let me get out the black pen. Covalent. Whoop. Alrighty, and there's a few different ways we can name this that I was accepting as far as your answers go. It's pretty lenient. Some of you just said nitrogen, which, again, we would normally say like molecular nitrogen. If you just said nitrogen, that's great. Molecular nitrogen. Or if you said nitride or dinitride. Ah. Let's just leave it at molecular nitrogen because this pen hates me. If any of those, I accepted them. But the main thing that we're really going over in this is your bonds and your electron pairs, right? So first things first, nitrogen. You should still remember from that periodic table that's in group 15. So 5 valence electrons. We're going to go ahead and plot those out. 1, 2, 3, 4, and 5. 1, 2, 3, 4, and 5. Right, so we're going to start off by drawing our little single bond between these two, right? And that's just going to share between those two. So that gives each one of them 6 valence electrons, right? But we want to have 8. So what we're going to do, share 2 more, make that 7. Share 2 more, make that 8. And then we're still going to have our leftover 2 on the outside. All right, so you notice every time we share, or every time we add go from a single bond to a double to a triple, we're increasing the number of valence electrons for each one of these nitrogens by 1, right? Because again, they're sharing. So started off with 5 and 5, a total of 10. And then we have 2, 4, 6, 8, 10. So we still meet our octet rule for both sides, and we've accounted for all 10 of our valence electrons. All right, so this should have been an easy one. Triple bonds, I get they don't come to mind often, but they were in our resources. We did learn about them. Triple bonds are the maximum, though. You can't have a quadruple bond between two things. Triple is about as high as they go. Up next, we have carbon dioxide. Again, a little bit of a freebie as to whether it was covalent or ionic. Again, it's all nonmetals. Carbon and oxygen are both nonmetals. A lot of you came to me with your little ion cheat sheet, and you said, where's carbon on here? I don't see carbon. It's because while carbon can form a -4 ion, it's very rare. It's not super common for it to oxidize. So this is a covalent compound. So first things first, we're going to look at our periodic table one more time. Carbon right here in group 14, so that's 4. Oxygen over here in group 16, so that's 6. Let's move back over here. So let's go ahead and draw those out. 1, 2, 3, 4. And then oxygen had 6. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So now we've drawn out all of our electrons, and we can count these out. 2, 4, 6, 8, 10, 12, 14, 16 total. So if we start off with our single bond between these two, we've only accounted for 4, right? So if we drew all these out as they were, so this would be if it was a single bond, which wouldn't be so bad, except for the fact that the octet rule isn't filled for literally any of these, right? So we're going to start off by trying to throw in a double bond or two in here. We know they're all unsatisfied, so we might as well throw a double bond on both sides. So we're getting rid of these 2 lone electrons we put down there. We're going to add boop, double bond on this side, double bond on this side, right? So we only moved them around a little bit. Keep in mind, over here, I forgot to draw them this time. I apologize for that. So we did the single bond here. I forgot to draw in those extra electrons for carbon, so I apologize for that. If I can edit it out later, I will. Knowing me, I probably won't remember to. So I apologize if that last bit was confusing. There were, if you recall, 4 valence electrons on carbon, so it should have looked like this before, right? So it would have had those 2, as well as these ones on oxygen. Before I drew those double bonds, it should have looked like this. So again, I apologize, right? So always make sure you account for your electrons. So we're going to go back through and we're going to erase them now, but those were there originally. All right, so I'm erasing 1 electron from each side of those, throwing in our bonds, so now we have 2 double bonds, 1 on each side. So let's go ahead and count these again. We have 2, 4, 6, 8, 10, 12, 14, 16. We've accounted for all 16 valence electrons, so this one's good to go. And again, I apologize for messing that one up. Again, these can be a little bit complicated. It's easy to make mistakes on this one, which is why I always want you guys going back and checking your work. That's why I check my work. That's how we catch mistakes, right? So up next is, again, this one tricked a lot of you guys, especially just from the symbol alone. This is PCl3, right? PCl3. The P is not potassium. Potassium has a chemical symbol of K. This is phosphorus. So we're going to look at our periodic table. Over here on the right side, we have phosphorus in group 15 and chlorine in group 17. Right? So again, this is not carbon and 3-iodine. This is chlorine. Right? So again, it can be a little bit tricky. This is an L, not an I. So if you did mess that one up, sorry, I guess I'll try to use a font that's a little bit clearer about it. You guys can always ask, especially during the retake, you can ask, is this an I or an L? That's something I'm always happy to help you guys out with. Right, so let's go ahead and start off counting or plotting down those valence electrons. We decided that phosphorus had 5 and chlorine had 7. So let's go ahead and do those. 1, 2, 3, 4, and 5. Right, and then let's count these for chlorine. We had 7, so we'll do 1 on its own and 3 pairs. Do that on each one of these. And yeah, I apologize. I know it takes a little while to draw all of these. That's one of the reasons you guys got 2 days. When it comes to the retake, I'll make sure that you guys have 2 days to do the retake as well. So we've plotted 7 on each of these chlorines, and we plotted 5 on this phosphorus, right? So we're going to start off with just a single bond between each one of these, right? Ta-da! If we go ahead and fill in our chlorines that we had here, we decided that chlorine had 7. We just shared one of them, so let's just throw on those 3 lone pairs here. 1, 2, 3, 4, 5, 6. And we'll do that for each one of these. All right, so if we went through and counted these, we decided that there were 3 chlorine that each had 7, so there's 21, plus 5 more from phosphorus gives us 26. So if we count this left side, you can pause and count if you want, but it's 26. Over here we have 2, 4, 6, and 8, 10, 12, 14, 16, 18, 20, 22, 24. 24 is not 26, right? We still have those 2 extras, but where would we put them? If you look at phosphorus here in the center, you keep in mind it had 5. So like we shared maybe these 2 over here, and these 2 right here, and these 2 right here. So there was still a pair of electrons that was attached to phosphorus. We didn't draw those, did we? So what we're going to do is we're going to draw those in now. So here's 25 and 26. Right? So now we've accounted for all 26 of those valence electrons. Right? We decided since they were both nonmetals that they are covalent. Would this be phosphorus chloride? No, it would not be phosphorus chloride. And the reason for that is, again, covalent compounds, they use Greek prefixes whenever we are naming them, right? So it's still going to be phosphorus. We don't have to use mono whenever we are talking about our like our first element in the compound. You can omit the word mono. It doesn't have to be monophosphorus. So phosphorus is fine for that. And it's going to be trichloride. Phosphorus trichloride. So again, it's covalent. It has 26 valence electrons, and this is what that would look like. Up next is molecular oxygen. Again, same thing with the nitrogen. There's a couple different ways that I would accept this written. I'm just going to type in molecular oxygen. In your elaborate assignment, that's the way it was named, so that was kind of the most commonly correct, like, frequent answer. Again, you could have said dioxide, you could have said dioxygen, you could have just said oxygen. Pretty much gave you guys the points for all of those. And again, in this picture, we're seeing here that they're sharing these electrons, right? So we don't even really have to go to the periodic table for us to know this is covalent. All right, so that was an easy one. Very last one, calcium chloride. This one should look familiar because I like to use those same types of examples over and over again, give you a chance to, if you know one, you know them all. It's going to look a lot like these up here, right? It's because we have a positive 2 ion and 2 negative 1 ions, right? If you're looking at your ion cheat sheet, you should be like, oh, wow, these are in the same rows, right? So first things first, it's a metal and a non-metal. So it is ionic. And we're going to go ahead and plot these valence electrons down just for, the sake of redundancy, where we'll go back to our periodic table. And here in group 2, we have calcium, 2 valence electrons. Over here we have chlorine, group 17, 7 valence electrons. Let's move back over here. Okay, so we'll go ahead and plot those. Zoom in a little bit, make it easier. We decided calcium had 2, and chlorine had 7. Again, I always like to put the lone ones facing what I know they're probably going to be bonding with. Just makes drawing them a little bit easier. There's no requirement that you do that. Alright, up next, we know this is ionic, so these electrons are being transferred somewhere. Ooh. So first things first, ta-da, we draw our arrows, right? So this represents where those electrons are going. So if we redraw these, chlorine, whereas it did have 7 valence electrons, it is now meeting the octet rule with 8. Right? Because again, it stole one of those electrons from calcium. Same as the example before, keep in mind calcium has 2 valence electrons, not 2 electrons, right? So when it loses those 2, the shell beneath it is still full, right? So it's still satisfied. You don't have to draw out all 8 of those, because again, we're really just tracking the valence electrons that we started with. But please understand that on this right side, this calcium, it's not without electrons. It has electrons. It just has a full shell. Again, it's just the shell that was beneath these, right? So if you look at our periodic table, over here on the right side. So here, left side, we'll start off with number 20, calcium. If it loses 1, it'll have the electron structure of potassium. Lose 1 more, it'll have the electron structure of argon, number 18, right? So it'll be full, just like argon is, and plenty satisfied. As a good student, you're going to do this right here, and you're going to include your charges. Again, I didn't take off points if you didn't include them, but it's a really good habit to get into when you're drawing ionic bonds, right? So +2 for calcium, -1 for each of those chlorines. And that pretty much sums it up. Hopefully this was fairly straightforward. I'm going to try to play this for you guys in class, so if you have questions, I'll pause it and you guys can ask your questions. But just in case you're not here or anything like that, I'll post these online. If you have questions, you can email me. I'll do my best to email back to you guys over break. I also want you guys to enjoy your break, so if you don't want to worry about this, you don't have to. But keep in mind, Tuesday when we come back, which is the day after we come back, you will be taking your retake, and it is a, take it the same time as everyone, or do not take it. So please make sure you guys are feeling confident and ready by that time. Again, when you choose to study is up to you, but when you take the quiz retake, that is already decided. All right. If I don't hear from you guys, have a wonderful break.